Now we want to derive some tests that will allow us to determine if a given series converges or not. And first, let's recall for a moment what we mean by the convergent series. So let's recall that the series sum from, let's say, 0 to infinity of an, that this thing converges if the sequence of partial sums converges. So if the limit sk goes to infinity of sk exists, where sk is a partial sum, so that's a sum from 0 to k of an. All right, so if I want to figure out if the limit of sk exists, then I can do that by verifying, for example, that the definition, verifying a definition of a limit for the limit here. And as you might recall, in that case, I would need to know what the limit of a sequence is, right? Because if I want to check the definition of a limit, then I have to show that for any epsilon greater than 0, there exists a capital K in this case, such that sk minus a limit is less than epsilon, and so on. In that case, I need to know the limit. And most likely than not, it will be very difficult to find the sum of the series, because you have to take a limit of objects like this. So first of all, you need to know how the partial sum depends on k, and that is going to be, in general, very difficult to determine. So then we have to try to appeal to a different notion that we discussed before, and a different notion of a sequence where you can talk about sequence converging, but you don't need to know what the limit of that sequence is. Because we're working here with real numbers, so an is a real number for any n greater or equal than 0. If we're working with a series of real numbers, then sk is a sequence of real numbers, and then that sequence is going to be a convergent sequence, as we proved, if and only if the same sequence is going to be Cauchy. So analogous to saying that the sequence of sk converges is a statement that sk is a Cauchy sequence. All right, so what does that mean? Sequence is Cauchy if and only if, or rather this is the definition of a Cauchy sequence, for any epsilon greater than 0, there exists a capital N in R, such that N, let's say greater or equal than M, bigger than capital N. This implies that Sn minus Sm must be less than epsilon, right? That's just a definition of a Cauchy sequence. All right, so that is fine. So as long as a sequence of partial sums is a Cauchy sequence, then my series converges, because if a sequence of partial sums is a Cauchy sequence, it is a convergent sequence. Fine. Now, what does this last statement mean? And I'm just going to continue writing it. So for any epsilon greater than 0, there exists a capital N in R such that N greater or equal than M bigger than capital N. This would imply, and now I'm going to remember what is S, let me see here. Let me change N to something else. Rather than using N, I'll use a different letter, L. Doesn't really change anything, right? Because I'm simply saying if I have two terms with an index which is larger than capital N, then the difference of these terms is less than epsilon. Okay, so what is SL? SK is given here. So SL is just the same guy, but the addition is up to L. So sum from n equal to 0 to L of AN minus sum n from 0 to M of AN. This is less than epsilon. Now, I'm assuming that L is greater or equal than M. So what does that mean? Still rewriting. For any epsilon greater than 0, there exists a capital N in R such that L greater or equal than M bigger than N now implies what? If I'm taking a sum of all elements of my sequence AN from 0 to L, and then I subtract a sum of all elements from 0 to M, then what am I doing? And M is less than L. What I'm doing is that I'm removing first M elements from this sum, which means that what is left is going to be a single sum from, now the first element in a sum from 0 to L that is not in a sum from 0 to M is n equal to m plus 1 up to L of AN, and this is less than epsilon. Now, when I'm writing here greater or equal, really when L is equal to M, then this thing is actually automatically 0. For L equal to M, really I'm not getting anything useful, so I can simply, L equal to M, this always is going to be true. So I can assume that L is bigger than M, and if L is bigger than M, that means that L should be greater or equal than M minus M plus 1, right? So if I have L which is greater than, strictly greater than M, then the first possible L that will fit into this is going to be precisely this L equal to M plus 1. So what I'm going to do, I'm going to say that my new M, I'm going to make M plus 1, I'm just going to shift M plus 1 by 1 up. In fact, to make this more transparent, let's just say P is equal to M plus 1. So I'm using a new notation. P is M plus 1, so then for any epsilon greater than 0, there exists a capital N in R such that L, now L was greater than M. So the first possible L would be M plus 1. But I just called M plus 1 P, so L is greater or equal than P, still bigger than N, right? Because if M is bigger than N, bigger than capital N, then M plus 1 is bigger than capital N. And this would imply that absolute value of the sum n from p to L of an is less than epsilon. So the conclusion from this computation is the following. If the series sum n from 0 to infinity of an satisfies this condition, then the series converges. Again, why? Because what did we do? We said that our sequence of partial sums is Cauchy sequence. So that means that the sequence of partial sums actually converges. So the series converges. But the fact that SK sequence of partial sums is a Cauchy sequence is basically analogous to the statement, right? Because I took the definition of a Cauchy sequence and I massaged it, rewrote in a bunch of different ways. At the end of the day, I ended up with a circled expression. So this is something then that I should be able to check to make sure that my series, that a given series converges. Now this condition that I circled here now has a special name. Basically, it is a condition which says that the partial sequence of partial sums is a Cauchy sequence. Then this says that you express it by saying that the sum of that the series satisfies what is called the Cauchy criterion. So Cauchy criterion is basically series satisfies the Cauchy criterion basically if and only if the sequence of partial sums is a Cauchy sequence. So there is really no Cauchy criterion per se. It is simply an expression of the fact that the sequence of partial sums is a Cauchy sequence. That is a Cauchy criterion. So that means that in order to determine if a given sequence series converges or not, I will need from now on to verify Cauchy criterion. Well, hopefully I don't have to verify it, but any test for convergence of a series that I will be able to derive should be a consequence of the Cauchy criterion. And one of the easiest tests is going to be this one. So let's call this a test for divergence. And the test for divergence will say the following. If the limit as n goes to infinity of an is not equal 0, which involves now two possible situations. Either the limit is some other number than 0, or the limit does not exist. So then the series sum from 0 to infinity of an, this does not converge. Or diverges, right? So let's try to prove this. And I'm going to prove the opposite statement. And the opposite statement is this. Suppose that on the contrary, the series converges. Now, if a series converges, then its sequence of partial sums converges. Then the sequence of partial sums is a Cauchy sequence, and so therefore the series satisfies the Cauchy criterion. So then and the Cauchy criterion says again I'm just going to paste it here. Okay, so if that is the case, then I'm going to take the situation where L is equal to P. Right, so for any epsilon greater than 0, there is a capital N, blah, blah, blah. So I'm going to take L equal to P, both are bigger than N. So in that case, what I have is that the sum N equal to P, L is equal to P, so from P to P of AN, this is going to be less than epsilon. But this is the same thing, right? So what am I doing here? I'm adding AN from P to P, which means that the summation actually only has one term, and that is AP. So AP is less than epsilon. So a sequence satisfies the Cauchy criterion. Then out of the Cauchy criterion, I'm only going to be interested in L and P that are exactly the same. And if I take L and P exactly the same and bigger than capital N, then my summation reduces just to a single term, AP less than epsilon. And so then what can I conclude from what I have just written? So therefore, for any epsilon greater than 0, there exists a capital N in R such that, and again, I'm looking at I'm not interested in all possible choices of L and P, I'm just looking at one P, such that if P is bigger than capital N, then what is the conclusion? AP is less than epsilon. Right? Again, for any epsilon greater than 0, this is capital N, such that if index P is bigger than capital N, then AP is less than epsilon. But if mod AP is less than epsilon, then that's the same thing, actually, as AP minus 0 is less than epsilon. And what we're looking at now is just a definition of a limit of AP as P goes to infinity. So therefore, a limit P goes to infinity of AP is equal to 0. Right, but if a limit as P goes to infinity of AP equal to 0, P is just a dummy index here, then I can also say that that means that the limit N goes to infinity of AN is equal to 0. Again, because it doesn't matter how you call your index. But what did I assume? So if the sequence converges, then that means that the limit is equal to 0. So if the limit is not equal to 0, as I assumed in my theorem, then a sequence cannot converge, because if it did converge, then a limit will be equal to 0. And so by using an opposite assumption, I proved my theorem. All right, so whenever the limit of a sequence that you're adding up is not equal to 0, that means that the corresponding series is not going to converge. Let's do a couple of examples of this test. This test is the easiest to perform, and that is something that you usually have to do first when somebody gives you a series, because it will be easy to show if the series is not convergent, because you don't need to, because the test is easy. So let's do an example number 1. Let's say I want to add up sum from 0 to infinity minus 1 to the power n. Well, so what is my an in this case? An is minus 1 to the power n, right? So I need to take a limit. N goes to infinity of minus 1 to the power n. This limit, as we know, does not exist. And if a limit does not exist, certainly it's not equal to 0. So that immediately says that this guy does not converge, because this limit does not exist, is not equal to 0. Right, so I applied the test of divergence, and it allows me to conclude here. What about the sum n from 0 to infinity, n plus 1 over 2n plus 3? Does this series converge? Again, let's take a limit. N goes to infinity of n plus 1 over 2n plus 3. Right, this is an indeterminate form, infinity over infinity. What you do in this case, you divide top and the bottom by the highest power of n. So because you cannot use properties of limits, you divide by the highest power of n, which in this case is n, and you get 1 plus 1 over n over 2 plus 3 over n. And as n goes to infinity, it's obvious that this goes to 2/3. Is 2/3 equal to 0? No. So by the test for divergence, again, this sequence does not converge for the same reason, because the limit is not equal to 0. Example number 3. Series n from 0 to infinity, let's say 1 over n. Does this converge or not? Again, I try to apply the same test for divergence. Limit n goes to infinity of 1 over n, right? That's easy. This is equal to 0. So then the question is, does this mean that the series converges? And the answer is no, because I know already, we proved it, that this is a harmonic series, and thus it diverges. But this limit is equal to 0. So what this means is that the opposite of a theorem that I just proved, right, that if a limit not equal to 0, then a series is not convergent, the opposite actually doesn't hold, because the limit of 1 over n is 0, but that series diverges, but the corresponding series diverges. So that means that the test for divergence only works in one way. That if a limit is not equal to 0, then a series does not converge. But if a limit is equal to 0, then you know nothing about what your series is doing. All right. Maybe one more example here. Example 4. What about sum n from 0 to infinity? Maybe 3/4 to the power n. Again, limit as n goes to infinity of 3/4 to the n, number less than 1 raised to the power n. We showed before that this limit is equal to 0. Can I then imply that my series here convergence? The previous example says no, right? Because the limit is equal to 0, it doesn't really tell me anything. The series may or may not converge. But in this case, actually, I look at the series, so I need to use some other test than the test for divergence, because if a limit is 0, it doesn't really tell me anything. And in this case, I see that this is a geometric series. With the multiplier, I forget how I called it, so r equal to 3/4. And this is less than 1. So therefore, this series converges. By the definition of a geometric series. And this means that the divergence test is inconclusive in this case. Okay, so then next time we are going to continue with more tests.